Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. For more than 40 years after the 1964 earthquake, the ground in southern Alaska continued to slowly move in a mechanism called postseismic relaxation of the upper mantle. The story begins with long-term sea level measurements using tide gauges. Instruments put out in coastal areas measuring every day the level of the water. And here are the observations in one particular study. This is in a place where there are other things that could influence the local sea level. We've seen influence where the 1964 earthquake caused large-scale changes in land levels. There are glaciers, there's a collision zone. So a lot of tectonic processes as well as things like melting ice that can change the local sea level. In Skagway, it appears that sea level is going down from 1940 to 2000. This shows this trend in the sea level from Larson et al. 2003. So wait, I thought global sea level was rising, not falling. Well, that's true. The average global sea level is rising due to rising temperatures and melting ice, but land masses on Earth can go up and down relative to each other, and this results in local sea level measurements on tide gauges being different. In southeastern Alaska, the removal of ice over the past decades and centuries means that the land is going upward and the local sea level goes down. This effect is strong in Alaska, but it is not the effect that we're focusing on for today's topic. Measurements of falling sea level can be used to determine the height of land. These time series show the compilation from Larson et al. 2003, and we'll look at one particular story that is expressed in these curves. Here's Kodiak, 1964, function of time on the x-axis. And in 1964, there's a big immediate change. And then over the decades, this curving uplift. So this will get into trying to understand the seismic cycle, illustrated for a subduction zone plate interface here. We see there's a downgoing plate here, a zone of large earthquake ruptures like 1964, which is typically locked. The two plates are stuck together during most of the time, but then break during the earthquake rupture. And satellites can measure these little points or GPS monuments on the, say, upper plate, would be Alaska for us, and measure the positions of these relative to each other. And we'll see that there are small motions that show that two plates are stuck to each other, or in the case of the 1964 earthquake, slowly moving in response to mantle effects. Here's the seismic cycle illustrated for a subduction zone from paper by Wang et others, 2012. And they label, so there's the upper plate, the subducting plate, and these different zones after slip, locking, relaxation. And they provide arrows of the relative motion of the Earth's surface relative to distant parts of the upper plate. So far from the trench, things are stable, but out in the region of the plate boundary, there are motions relative to the interior, which represents some kind of deformation of the material. So here the earthquake cycle is the sum of these first three. And I'm going to adapt this a little bit, slightly different order. And so this is what we'll be working with. So number one is the rupture, where the upper plate moves to the left during the rupture. Number two is going to be what's called after slip, and we're going to focus on mostly the lower stretches, but can also occur above the boundary where the rupture occurs. Number three is locking, so the plate relocking after the earthquake. And number four is going to be relaxation of the mantle. So the mantle basically gets kicked during the earthquake and it takes a long time to move. So we're going to break these down one by one. But first is the earthquake rupture. The plate becomes unlocked, and in moments, the edge of the upper plate here jumps to the left. takes maybe seconds to minutes, but this would be such as what's happened in the 1964 earthquake. That's the earthquake rupture. Aseismic afterslip, the word afterslip means basically slipping after the earthquake, occurs mostly above and below the earthquake rupture zone. This can happen in days to months, but there's basically kind of expansion of what happened rapidly in this zone. There's also some slip that occurs above and below in the places that are not locked, at least not as much during the earthquake cycle. And here's a picture that combines both of these for the 1964 Alaska earthquake and the afterslip. The red shows imagine this shallow dipping subduction zone. So we're kind of looking on top of the thrust interface here. The trench would be out here. And what you see in red is showing the co-seismic inferred slip. So slip up to 20 meters you can see in these patches. So the inference of how much co-seismic slip is needed to reveal the kind of vertical deformation that we've previously saw in the 1964 earthquake is shown in the co-seismic, and the afterslip is shown here isolated much deeper down, so below on the interface, probably 60 kilometers to even 100 kilometers depth, deep on this interface, there's significant slip that occurs. And these blues are up to 4 meters. So you have these two different episodes, the co-seismic and then deeper down, this afterslip that occurs in days to months afterwards. So it's a really interesting example of trying to break down that the earthquake cycle isn't just a light switch on and off. There's a lot of different processes going on that were illuminated for the 64 earthquake. The third is that the interface becomes locked again. So shortly after the earthquake, this contact becomes locked. And when that happens, the upper plate is stuck to the downgoing plate. And so the motion of the upper plate is essentially moving to the right relative to the stable interior. And that's picked up by modern measurements of geodetic deformation. But the fact that this is moving relative to the interior tells us that this boundary is locked again. So during most of the earthquake cycle, the surface motion is dominated by this mechanism. And the last one, which is the focus of this talk, is viscous relaxation of the mantle, which occurs in the months and years following the earthquake. Part of the reason is that mantle rocks move slowly. So there's this dramatic episode of the earthquake happening, kind of abrupt motion, and the mantle material on both the oceanic side and in this mantle wedge under the upper plate, they get perturbed, and it takes a while for the rocks to relax back to the places what they were in before the earthquake. And so this has resulted in the upper plate moving, in this case, slowly to the left, and in the subducting plate, potentially, if observable, to the right. And this is the fourth part of the cycle, the thing that takes much longer. And this is the observation from Kodiak. So in the decades following the 1964 earthquake, the tide gauge uplift data at Kodiak can best be explained by the combination of background interseismic signal. So this B, this red line here, would represent the interseismic locking of the plate interface. That would be expected for any large subduction zone being an island on the upper plate. A is the afterslip, shown here as this dashed line, which is mostly involved in the sort of 15 years after the event. You can see this curve, this portion of the signal that's been estimated by these authors. And the last part is the afterslip, sorry, the viscoelastic component, this V, which is this more subtle signal right here, but it's still, from these authors, something like 15 centimeters over decades. It's easily measurable by these kinds of data. So here you have one signal, and the blue would represent, you'd want this to be zero if all the effects were accounted for, where you take the observed and you'd subtract the viscoelastic part, the afterslip, and the background part. You'd hope this is going to be about zero if your modeling is correct. But this one decades-long tide gauge provides compelling evidence that there's this very long-term, 40 years later, viscoelastic effect showing that the ground is still moving in response to the mantle being kicked in 1964. Takeaway topics: surface deformation from large earthquakes continue for months, years, and even decades. Today, surface deformation is measured by continuously recording GPS and by satellite imagery. Tide gauge measurements can be useful to infer uplift patterns over decadal timescales. The seismic cycle contains 4 parts: earthquake rupture, that's called postseismic, after slip, locking, which is really the interseismic part, and viscous relaxation. The 1964 co-seismic slip was up to 20 meters across the plate interface and occurred within minutes. The 1964 after slip was up to 4 meters and occurred over years, primarily deeper down on the plate interface. So thank you for watching, and please stick around for supplemental material.